When we go down to the microscopic level, an interesting principle arises that waves and particles are really fundamentally the same thing, and that a particle is a wave and a wave is a particle, and so we have this wave-particle duality. This idea, this concept, leads to a couple of fundamental relationships that are important to think about as we're moving forward. So first of all, let's just think about the consequences of a particle being a wave. So if a particle is a wave, then that means that it doesn't occupy a discrete space in our world. So it doesn't have a particular position. So it has no discrete position. Or we can kind of think of it as being smeared out in space. Very technical term, smeared out. So no discrete position, because we know that waves don't exist in one particular place in the room. They're smeared out throughout the entire room. And it means that it must have, if it's a wave, it has a wavelength and a frequency associated with it. Likewise, if light is a particle, then that means that we can locate it in a region in space. So it must have some region where it is located. And that means that it must have a momentum associated with it, because particles have momentum. So these two ideas, so notice that these are sort of the flip side of each other, and these are sort of the flip side of each other. These two ideas lead to two important relationships, and we're going to examine those two relationships now. So the first idea is that if a particle has a wavelength and a wavelength of light has a momentum, then wavelength and momentum should be related to one another. So this idea came from de Broglie. And the de Broglie relationship is that the wavelength is equal to Planck's constant. So h is Planck's constant. We're going to see this a lot because this is the fundamental constant that connects waves and particles. So Planck's constant divided by the momentum. So that means that if we know the wavelength of light that we're talking about, we can calculate an associated momentum for that light. And if we know the momentum, mass times velocity, of the particle, we can calculate an associated wavelength for that particle. And so this relationship is a very important one that connects wave properties, right, to particle properties. So particles have momentum, waves have wavelength, and this connects the two things. The other relationship that is really important that is a consequence of this wave-particle duality is the uncertainty principle. The uncertainty principle states that we cannot know the position x and the momentum p to the same precision. So in other words, the uncertainty in the position, so our plus and minus uncertainty. So if I know the position of the particle to within 1 millimeter, then delta x is 1 millimeter, right? I know it that well. I plus or minus 1 millimeter, right? And delta p would then be the uncertainty in the momentum And so these uncertainties, the ability to measure x and the ability to measure momentum are related and cannot be smaller than h bar over 2. So h bar is Planck's constant divided by 2 pi. That's also a constant that is going to show up frequently, because oftentimes we have this factor of 2 pi that everything gets divided by, and so we just fold that into Planck's constant and call it h bar. So these two relationships, de Broglie's relationship and the uncertainty principle, are important relationships for connecting waves and particles. Let's look a little bit more at the uncertainty principle and get a feel for where this comes from. The first thing we need to do is to think about how we actually observe things. And so if you think about some object that I'm trying to observe, I can only see, so let's draw a little eye here. I can only see that object if there is light that is bouncing off of the object and into my eye, because my eye detects the light that is scattered by that object. And so I have to shine light on an object in order to see it. So let's say that I have a particle in my room and I'm trying to measure, or maybe it's on a table, right? So let's put it on a table here. And I'm trying to measure where that particle is located on that table. So in order to do that, I'm going to observe that particle here. And I have to bounce light off of the particle that bounces into my eye so that I can see it. Now, it turns out that if you've ever used a microscope, you know that in order to see an object in a microscope, the wavelength of light that you're using has to be comparable to the size of the object. Because if the wavelength is not smaller than the size of the object, then you're actually going to see diffraction off of that particle, and you're not going to actually see exactly where that particle is. You're going to see a diffraction pattern. And so in order for this to work, the wavelength of light has to be smaller than the size of the particle. Okay, so if I want to see this particle, and let's say that this particle is a hydrogen atom, so very, very small, on the order of 10 to the minus 10 meters, right? That means that I need a wavelength that is less than that size, right? I need a wavelength that's very, very small. Okay. So we know from the de Broglie relationship that if a particle has a wavelength, or light has a wavelength, it also has a momentum. And so the smaller the wavelength, the larger the momentum. Okay, so if I send light with a high momentum, with a lot of momentum, and bounce it off of this particle, it's going to move the particle. There's going to be a transfer of momentum to the particle. So the very act of trying to see where this particle is going to move the particle. And so depending on how much momentum I can transfer, the particle is going to move more or less. And so the uncertainty, how well I know where this particle actually was, is going to depend on how big my momentum is. My momentum, how big the momentum of my light is, depends on the wavelength. And the wavelength that I need in order to actually see that particle has to be smaller than the size of the particle. And so we run into this fundamental problem where simply trying to measure where that particle is changes its position, makes the position more uncertain. And if I try to get the position more certain by using a smaller wavelength, then I have more momentum, and the bigger the momentum, the bigger my uncertainty in the position. So this depends on the momentum of the light, which depends on the wavelength of the light, right? And so the more I try to measure the position with greater certainty, the less I know about it, because I have to use light of a higher momentum. And that leads to the fact that the uncertainty in the position is related to that uncertainty in the momentum. Because if the particle is at rest, I know that it has zero momentum, and I know exactly where the position is. If the particle is not at rest, if it's moving, then I'm not as certain where it is, and I also don't quite know what its momentum is. And so this leads to this uncertainty principle. And notice that it relied on our understanding of how wavelength and momentum, the de Broglie relationship, is also important. So that's a little bit of a thought experiment for where that uncertainty principle comes from, and why the very act of measuring something changes how well we can measure it. And that is a concept that is embedded into quantum mechanics, and a concept that makes the whole proposition of doing measurements and observing things really, really interesting, because the smaller the system gets, the harder it is, and the more we have to worry about this this way in which our observations change the state of the system.